Bismillahirrahmanirrahim. Assalamualaikum warahmatullah. So we continue to the next part of part B, frequency modulation. So this is again the chapter guideline. We have done frequency modulation introduction and the derivation of frequency modulation equation. So today we will discuss about the frequency spectrum of FM signal. We have seen FM signal involve sign of a sine, the equation. The solution of this expression involves the use of Bessel functions. The expression of the FM signal can be written as Vfm t equal to A J naught mf sine omega c t plus J1 mf column sine omega c plus omega m minus sine omega c minus omega m plus, a column, plus J2 sine omega c plus 2 omega m minus sine omega c minus 2 omega m plus J3 mf sine omega c plus 3 omega m minus sine omega c minus 3 omega m plus etc. Thus, the spectrum of FM signal contains a carrier frequency component and apparently an infinite number of sidebands. So this is the sideband J, J2, J3, J1. J1, J2, J3 is the sideband. In general, Jn mf is the Bessel function of the first kind and n order. It is evident from this expression that it is the value of mf and the value of the Bessel function that will ultimately decide the number of sidebands having significant amplitude and therefore bandwidth. For the following observation can be made from this expression just now. For every modulating frequency, the FM signal contains an infinite number of sidebands in addition to the carrier frequency. So the FM signal contains the carrier frequency and infinite number of sidebands. Where in AM signal, there are only 3 frequency components, which is the carrier and 2 sideband, which is lower sideband and upper sideband. Number 2, the modulation index determines the number of significant sideband. The higher the modulation index, the more the number of significant sideband. Okay. So this is the equation that have been derived previously in previous part of the video. Vm equal to Vc cos omega ct plus mf sine omega m t. So this is what we call cos of a sine, sine of a cos, sine of sine, cos sine omega mt. So this equation involves the Bessel function. So solving this equation, Vc cos omega ct, this part, bracket mf, this part, Vc cos mf, this one, darab, multiply, mf sine omega mt minus sine omega ct bracket mf sine omega mt. So this is the equation where we need Bessel function to solve this equation. Okay. By using mathematical expression, solving that equation will give this long equation. The above equation, the FM waveform, has a component at the carrier frequency. This is the carrier component, omega c. Omega c is the carrier component, and unlimited series of frequencies above and below the carrier frequency. So unlimited series frequency, we call it sidebands. Above the carrier frequency is this one, positive, 2 omega m, 4 omega m. Okay, and below carrier frequency meaning the negative part of that frequency. This one, omega c minus omega m, 2 omega m, to minus 2 omega m, and so forth. So we have the carrier frequency and unlimited sidebands above and below carrier frequency, where Jn is the Bessel function for first type and order. J0 will give the amplitude of the carrier. So J0 is the amplitude of the carrier. Jn will give the amplitude of the sideband. Jn from n equal to 1 until n, the significant value of sideband, will give the amplitude of sideband with the frequency omega c plus n omega m. An important characteristic of Bessel function is j n equal to 1, j square n equal to 1. Okay, so this is the important characteristic of the Bessel function. Actual amplitude for the sideband is Jn multiplied by Vc. So Jn is like a constant multiplied by the amplitude of carrier signal, Vc. Or Jn is the relative amplitude of the sideband. We need to multiply Jn with the amplitude of carrier signal to get the actual amplitude for the sideband. We will see this later. So this is the frequency spectrum, or the frequency domain of the FM signal. So this is the amplitude of J. We have J0, J1, J2, J3. So this is in pair. The sideband is in pair. So the signal also in the same range for positive and negative. So we have here J0 at Fc is the amplitude of the carrier at the carrier frequency. J1 is the first sideband with the amplitude of J1 at the left and right side, or at the below and above of carrier frequency, and it is at the frequency of, at the above it is Fc plus Fm, and below is Fc minus Fm. This is the first sideband. And we have a second sideband, J2, at the second band, which is Fc minus 2 Fm, and at the above, at the upper sideband, we have Fc plus 2 Fm. So, and so on and so forth. We have this J1 up to Jn. So spectra of FM signal for different values of modulation index. So the value of modulation index determine how much the sideband of the FM signal. So if we have modulation index at equal to 0.2, we have only one one down and one upper. Okay, if we have moisture index equal to 1, we have two below and two above. If we have moisture index equal to 5, so we have so many of side bands above and below the carrier frequency. So how we determine this? This one we can determine from the table of Bessel function. For every modulating frequency, the FM signal contains an infinite number of sidebands in addition to the carrier frequency. Okay. In AM signal, there are only 3: carrier, lower and upper side frequency. Number 2, modulation index determine the number of significant sideband. So the value of MF determine the number of significant sideband. The bigger the value of modulation index, the more the number of significant sideband. The sideband distribution is symmetrical about the carrier frequency. So sideband distribution is symmetric at the FC. The pair of sideband frequencies for which Bessel function has a negative value signifies a 180 phase change for that pair. In the case of AM signal, when the modulation index increase, so does the sideband power and hence the transmitted power. In the case of FM signal, the modulation index increase, the sideband power increase. However, it does so only at the cost of carrier power, so that the total transmitted power remains constant. This is the Bessel function. Variation of carrier and sideband amplitude as a function of modulation index. This is the modulation index, and this is the amplitude, and this is the modulation index. So we can see from this figure that the more the value of modulation index, let's say 0, so there is only one the carrier, the amplitude. If we have 2, then there are so many sidebands, J1, J2, J3. And if we have the modulation index equal to 8, we have all those J1, J2, J3 up to J6 and above. So the higher the value of modulation index, the more the sidebands, it will become significant. Okay, that's all for now. We will continue a little bit more on Bessel function in the next video. Thank you very much.